we had already solved for K last time. So now we are working on solving for T. I have a bunch of calculators that I took home by accident. So who needs a calculator? You want one? You need one? We're dividing by the negative 0.0002. Put a point right there. And it's not right. You're not adding. You're dividing by the negative number. Yes. All right. Did you get about 10,000 years? Oh, I just gave away all my calculations. All right. I am taking the natural log of 0.3 and dividing by that K value, and I get about 10,000 years. 10,033 years. And look, 2 half-lives would have been about 11,000 years, right? On less than 2 half-lives. Because I still have 30% or 30 grams left. If not, I would be only down to 25% or 25 grams left. All right, so 10,033 years. T equals 10,033. Okay, so I'm going to skip Newton's law of cooling for just a minute because that formula is slightly different. And that's the one that I'm not going to put Newton's law of cooling on your test on Thursday, but we are going to use it on Friday when we do the hot cocoa cooling experiment. So I'm just going to skip that one for a minute and jump over to question 1 on the next page, which again did not print very clearly. So let me just, how long does it take to go from, I'm just going to pick 100 grams down to 50 grams. So we're going to plug in 100 as our starting value and 50 as our ending value because those are easy values to use. I could have picked 12 and 6, or I could have picked 2,000 and 1,000. Just whatever you're starting with, if it's a half-life, you end with half of the amount. And the first step, when you divide by 100, you end up with 0.5 right here. That's how you know you're dealing with a half-life. So I'm trying to solve this equation for T. How long will it take to go from 100 down to 50? So my first step, I divide by 100 on both sides. So I get 0.5, this is supposed to be an arrow, 0.5 equals E 244T. All right, and now I'm at the same step I was in the previous problem. What happens when you're stuck in exponential form? You rewrite it in log form. So I'm going to rewrite, it's always going to be the natural log. Because it's always going to be the log base E of whatever number you had, in this case it's half, equals negative 0.0244T. So you're going to catch on, and you probably won't have to write out all the steps eventually. You're going to take the natural log of the number and divide by that K value. So that's the LN button. So on your calculator, it's right underneath log. See how natural log is right there? So you're going to type natural log of 0.5. Or you could use the change of base key too. So if you forget where it is, if you go under that math key, log base, you can change the base yourself to E if you want to on the test. To me, it's just a shortcut knowing that the natural log is a base of E. I'm going to take the natural log of half and divide by that. I think that I did last block. Oh, they're right behind this fern that I probably will throw in. Oh, look at it. So I do have a pot of dirt in my trunk that I put. I'll recall that where. I actually dumped the frozen right, what did I get? I got, yes. Oh, did you say 28.4 or 20? Good. So you got it. So you type ELN button, 10.5, then a little parentheses, and divide by that. All right, so we got 28.4 years. All right, so let's see if we can set up the next one. 28.4 years. All right, so this time, a culture obeys the law of uninhibited growth. All that's saying is that it is okay to use this formula. That's called the law of uninhibited growth, where you've got a K value. Okay. It says there are 500 bacteria initially, and there's 800 after 1 hour. Okay, so that's the first part of my question. We need to solve for K using all that information. Part 2 of the question says, how many will be present after 5 hours? I can't figure that part out until I first solve for K. So we're going to use, this is, you could write it out just to practice, like that's the law of uninhibited growth. A equals A sub 0 e to the kt. Now I'm going to plug in what I know. What was my initial bacteria population? It was 500, right? That's my initial value. My ending value was 800. So 800 is my ending value. 500 is my initial value. E is just E. I don't know K. That's what I'm solving for. But I know that it took 1 hour for T. So you're going to solve for K the same way that we've been doing it. You're going to first divide by 500 on both sides, and then use the natural log to find the answer. So I don't know what is 8/5? 1.6. So 800 divided by 500 is 1.6. 1.6 equals, I could just write e to the k, right? Because k times 1 is k. So I'm changing this into log form. The base would be e. See if you can write that out in log form yourself. Log base e of 1.6 will actually give me k. I don't have to divide by anything. All I need to do is take the natural log of 1.6. But that just gives me my k value. I haven't actually solved the problem yet, right? K is 0.47. How do I know k is positive? Why does it make sense that k is positive? Because what? The bacteria are going up. Your k value will be negative if you're decaying or decreasing in population, but my population is going up. So my k value is going up. Now that I have k, now I'm going to use it to solve the rest of this problem. If you're out of room, you could use kind of the bottom of the page here. We want to figure out how many bacteria there will be after 5 hours and how long will it take the population to reach a million. If you want to type this into your calculator and use the table, this would be a good problem to use the table for. So you would type into your y equals menu that we're starting with 500 bacteria, e to the 0.47x. So if you type that into your y equals menu, can you answer those two questions? What's the population after 5 hours? And how many hours until you reach a million? Right? Because we know what K is. See if you can practice using your table, because we haven't been here in a week using our table. What time do I have lunch? 50? No. 49. Okay. Then we can do Newton's law after lunch. Did you guys do this scientific notation puzzle? Did I give it to you? Must not be in this packet. Use your table and, okay, well, this would be a good practice for maybe later this week. Maybe you could do it as a warm-up. All right, you're plugging that into your y equals menu and answering those two questions. I know you can do it. I'm going to do it too. 500 e 0.47x. 5 hours should be easy, right? You just pop down to the 5th hour. And then 1 million is after how many hours? You can just go to the nearest hour. Anyone need help typing it in? Oh, go back to the second. Okay, so you go to second table setup. Oh, wasn't it? What was there? Point 47. Okay, now go to the second table setup. Let's start our table at 0 hours. Start at 0. Count by 1. That's good. This is on auto. Auto. Arrow up and hit enter. Then go to second table. So then if you want 5 hours, and know what population is, and you can see when the population will reach 1 million, how many hours that will be. Did you get it to work in the table? Yeah. So 5 hours, that's the population, and then you can look for 1 million, how many hours would that be? Okay, good. So you got it. You got it to work out on the calculator. Did you get on the calculator? Great. You in charge of this account? Yes. And then do you try ever guessing passwords on Instagram? No, I always just reset one if I don't do it. I know. I hate when you log out on all your devices. Like my phone is just on my by your phone, it logs you out. Like, oh wait, no. It doesn't if you connect it to your Apple ID. Yeah, but I don't have an Apple. So like it transferred all my apps, but they were not logged in. And there's some accounts that I never use. So I have to like, you gotta re-log in. All right, so you should have gotten, I just rounded to 5,243 bacteria in 17 hours. So you're just scanning in your table, right? So at 5 hours, it tells you the population, and then I scroll down to 1 million. Okay, let's do one more on this kind of half-life, and then we'll do Newton's law after lunch. Okay, so this time they're telling you the half-life is 1,690 years. That's all the information you need to solve for K. It is a half-life, and that's the T value. We want to find the K value. Then, once we know the K value, if 10 grams are present now, how long or how much will be present in 50 years? I can't answer the question until I find K. So I'm going to set up A equals A sub 0 e to the kt, and I'm going to fill in what I know. I'm going to pretend again I'm starting with 100 and ending with half of the amount, which is 50. I just always pick 150. It's easy. E stays E. K, I don't know, but I know the number 1,690 is T. So your first step, divide by 100 on both sides. That's always going to be your first step. 0.5 equals E to the K times 1690. So you're ready to transform it into log form and then divide to solve for K. Are you good with how to go to the next step? We've done a couple of them. Right? If E is the base, then the base of your log will be E. And then these two numbers flip-flop. So the 0.5 goes inside the log, and all this stuff in the exponent, K times 1690, goes outside the log. So you should be on this step in solving for K. Take the natural log of a half and divide by 1690. Natural log of a half divided by 1690. This comes out in scientific notation. So your calculator reads -4.1 E -4. That's scientific notation. So it's -0.00041. It's telling you to slide the decimal 4 units to the left. I would just write it down like that. -0.00041. It's a really small K value. That's why it takes so long to decompose. -0.00041. I'm going to use that K value. And if you want to do that using the calculator, you could. Okay? You could keep your equation in the calculator. So let's type in. We're starting with how much? 10 grams are present now. 10 E. I know my K value, -0.00041 X. Right? So that would be my equation. And I would go to year 50 in the table. And that's the same as plugging it in by hand. Or you could just type it in and plug in 50. Right? We have our K value now. We're plugging in 50 years and seeing how much is left. We know it's less than 10. It's going to be a lot left though, because the half-life is 1,000 years. We've only gone 50 years in the future. So it's going to be like 8 or 9 grams still. So if I go to table setup and jump to year 50, you guys know how to jump to year 50? And then see what you would get in the table. Yep, it's 9 point something grams are left because only 50 years have gone by. See if you can figure that one out. So it comes out to 9.8. Did you get 9.8? So I know we have 4 minutes, but could you try, I skipped all the way to the review, page 411. Some of you started it and some of you didn't. Could you try question 22 in these last 4 minutes before lunch? They're giving you the half-life. This is number 22 on the last page in like the whole packet. Number 22 on the review. You're going to use this information to solve for K, then do this part 2 after you solve for K. So you're going to use the half-life, solve for K, and then see if you can. This would be the hardest question on the test on Thursday. It would be a half-life question like this. So could you do a question like this? And I will give you this formula. So this formula, those will be printed on your test. So see if you can do 22, and I'll give you a couple minutes when we get back from lunch as well. This would be like, do I do a half-life question? 14 is going to be T. And 80, you're going to use that as 50 and a half. Ignore the 80. You're going to get K. K. We don't know K, but we know T is 14. Yes, yeah. And oh, she's writing her post. Oh, she signed in Instagram. Right? Try this question, number 22. Go to another page. 22. You got a couple minutes to try it now and a couple minutes when we come back from lunch. This is the like, aha, I can do it. Because I'm going to show you Newton's law after lunch. So this is when you're starting with 100 and ending with 50. Half-life, you always start with 100, end with 50. Because that makes the math easy. If you start with 13, you'd have to end with 6.5. That doesn't make for very easy stuff. So start with 100. Where's Kate today? You put it in like a log. Yep. Divide by 100 first. You do that first. If you can get that process down, I think that process is the hardest part of using logs. Yep. Yep. K, or 14K. 14K. No, 13 multiplied K. And that would be the K. Then you get the second half of the problem. But you'll at least get down to K before you move on. And part 2 of the problem will be back. That's it. You can do those steps. You're doing the hardest part is solving the logs. Although for you guys,